Do you ever wonder? Do you ever wonder? Uh, sometimes looking at a piece of code, what must have been going through someone's mind that they would write down something in a certain way. When I mean, really, it makes no difference. But I mean, this is totally safe. But why not? Why not just do this? Address of that. Then you don't need to set it. It's automatically set by the operating system. You might even set this to 0, just in case. I think the default is 0, but you never know. Also, this pointer shouldn't be modifiable, right? And why is it even a pointer at all? Why not let it be a reference? You know, this could have been, where is it, defined. Static long ref. Object count. It can be a reference to a long, right? I don't know why, but he says he doesn't want it inside some framework. Now I wanted to actually look at this to make a point about multi-threading, and I suppose that this example is quite familiar, and you'll see this sort of thing all over the place. And it just demonstrates that the standard naivety when it comes to multi-threading. The dangers of multi-threading is so dangerous, and it's so easy to make a mistake. There's an error, right, in this function that could cause a crash. Okay. So funny. But I don't blame them, because it's hard to wrap your head around the fact that a whole bunch of little processes are going on, and you know, jumping inside this same function while you might be the thing that you thinks that is you identify with yourself as you're walking through and writing code. One sort of imagines there's a me involved in this, right? Okay, decrement the reference count, right? Let's imagine that I've given this, I've been giving this object to various other parts of my program, and it's being used in various different threads. Okay, presumably that's the situation. If this is in a multi-threaded environment, it certainly could be, according to the way this is set up, right? Deriving from the thread model. Okay. First off, increment is supposedly thread safe, and it probably is, but partly thread safe. Increment in the multi-threaded world is an interlocked increment. You could look up the help. One could look up the help for this function if one wanted to. Now this returns the resulting incremented value. Alright. Now, if it returns that, then, well, why not just return the result of running this function? As it is, it's not safe to access this variable at any time, right? Because other threads might be writing to it as you're reading from it, and that can cause a crash, right? Multiple access to the same memory location. So right here, here's one bug. This is a crash. You have to always keep in mind that anything that is this is not necessarily global, this variable. It can be. This function is used for globals and for local in terms of the object. But local in terms of the object is still a type of global. The only thing that's truly local is something on the stack. So this line has to say this. There's no other way to write this and not ask for a crash. Similarly, this has to do the same. And by the way, the thing being returned is on the stack, so it can't be touched, right? Every thread gets its own stack. So the result of this operation being done in a thread-safe manner and being copied onto your stack in a thread-safe manner gives you provides you with a value that you can return or do something with, like returning, and not worry about any other thread accessing it. You could also do this, and you can use L result. That's safe too, because it's on the stack. The last thing you can touch is this thing. That would be that will lead to a crash in the end. This is much simpler, of course. That's one danger. Now again, even though it's say this increment we've now fixed, and it is not going to cause a crash. This function has now become thread safe, and this assignment is thread safe again because this is on the stack. So why are we using this non-thread safe thing in a printout? I think I put this in. It should be UL result, or ret. That's safe. The other wasn't. Similarly, this quantity, or this variable, is volatile and can't be touched without any synchronization, protection. So we could say ULG ret or something, global ret, and safely use that in this printf. Now this function is thread safe. But before that, it would have been a crash. Oh, no, not yet. Unfortunately, here we are accessing again a variable that we're not allowed to access. However, this doesn't mean we're completely in the dark. Whatever the return value of this function is, we can assume, and it's only an assumption, it's not a truth, but we can assume that the previous count was this value minus 1, right? It's a guess, but this is a debug printout, and similarly, this here. There's no other way to go about it, because we're not allowed to touch those variables other than through some manner which is thread safe. We could put a critical section around all of this, and that's fine too, but there isn't, so therefore we have to do the next best thing, which is to use only stack data. Stack data is thread local storage. Maybe I could call this LRET, local and global. How about this? How about ret? Ret G. How about that? I think that's a little bit clearer. It separates the meaning and the scope by an underscore. Local, global. But that is just a guess, right? You can't know. There's no telling what this value is. Was before this line was executed. It could have been 20, 30. From here to here, you always have to do this in your head. Imagine that there's a task switch, right, just before this line gets executed. No, sorry. How do I say? Now we're going to call this function, and so there is some value in here. Okay, at the time of the call, a value is pushed on the stack, right? What that value is what it was at the time of making the call. Now, I don't know how that is thread safe, but the processor, I think, sees a push instruction as an atomic instruction. Like increment, I think, might be an atomic instruction. It has to be possible to push something Otherwise, how do you how are you going to get into pass a value? Now wait a minute, why is this not a pointer? Oh, it's a reference. Should be a pointer, really, because anyway, just for readability, reference it's harder to read. Anyway, it's got to be possible to push something on the stack, or else there would be no way to get to the incrementer thing, right? Unless these calls are somehow, oh, it's an address, it's an address. The address never changes, that's right, okay. So this is fine because the address of this, that's why it has to be a pointer. See, you gotta think about these things. It has to be pointed out to the person calling that an address is being put on the stack, not a value. The value is subject to change. The address is not. Yeah. These two should be pointers, even if it's single-threaded, just for consistency. This is single-threaded, apparently. And this has to say star. I didn't mean to come here and clean this up. I just can't help myself. It's wrong. Well, it's not ref1, it's PTR. Okay. Now this doesn't need to do anything. These are not pointers, so we make them pointers, and the return values. The return values are not pointers, but numbers according to the help. Return value, the resulting incremented or decremented value, but it takes a pointer. These longs have to be declared as volatile. Where are they declared? Being passed in. Okay. Well, it's doing pretty good now. There's a 10% chance maybe that this function will crash. No, I think it's guaranteed now. These are on the stack, they're safe. All this is safe, and this is on the stack and it doesn't exist. Which one was it? That's the uret local. Same with this. Decrement. Now, again, I have to ask myself, here it looks like he started to do the right thing, put it on the stack for safety. He never uses this value ever again. And why are these longs and the others are u long? I think either something changed. U ref G. Value. Total object count is, well, maybe, there's a chance that it might be equal to this return value. This object count might be equal to that, minus 1, plus 1. No, current count. All this is before. So before is plus 1. And then there was, we presume a decrement occurred. And now we'll just print out these. This is just making up stories, right? Because we don't have any access to these variables. We certainly don't have any access to this variable mcref, right? Ever. Right? Following this point, there are no variables in the class that we're allowed to access following this decrement. Even like critical section protected, you can't. As soon as this line occurs, is executed. Suppose the return value here is 7. Okay. Now imagine a task switch occurs, and 1,000 years elapses. And now we're ready to start again on this line. Well, in that 1,000 years, do you think maybe the object is still alive? Probably not, right? So, but as soon as you decrement this thing, you are instructed to consider the object deleted already, right? So you certainly can't touch this. But this return value, if it's 0, okay, then there's no chance that another thread will see this decrement result in a 0 return. There is no chance of that occurring. That's the one case where you're allowed to actually look at the data, because this is just one object, right? That was created through some constructor. This should be a 1. Everything's wrong. Now, how did that end up being a 1 and a 0? And I know at some point later on it's a 1. You have to start at 1, okay? Because then the object won't suddenly get deleted on you, and you don't want that. Once it's 0, though, having been a non-zero value, then that means that the only reference to this object at the time of this decrement was the current one that is executing this function, and there's nothing in this function that is handing this object to someone else in this thread, and no other thread has a view of this object, this particular object. Like it's not in any other storage area. If this had returned 0, let me think now. trying to imagine a way in which somebody else might actually have have bumped it up again or something. The same object can't. Somewhere in the code there's a line that says, release. And on the left-hand side there is a variable. It can be it is the only variable containing this pointer, the particular pointer, that's running this function. Because if any other variable happened to have those same digits in it, then this count could not have been 1, right, at the time when they went to 0. Unless, of course, somebody was doing the dumb thing of not immediately trashing something that they release. As soon as you release something, you must trash the memory containing that information, right, in your own thread. So therefore, in the case when this goes to 0, assuming everybody else is not doing the stupid thing, it is in fact safe to look at the other variables, strangely enough, but only if this returns 0. Now, if it didn't return 0, then we can't look at anything. If it did, yes, actually this is safe. It's safe to look at this because no other thread will delete it. So you can do this, and you can certainly return the value on the stack, even though the object's been deleted. The stack hasn't been deleted. Now this has to become 1 here. Now, how come it's not 1? Where does it get? Let's see. No. Somebody must be incrementing it on construction. When does one of these things get constructed? That's tough. I don't know where I've cut in on that on this video. Probably where I started discussing or searching for the where that 0 turned into a 1, and I was just watching to see, trying to decide whether or not to upload. I think there are some good points, so I should probably upload it. But I did find the line, and here it is, where that 0, the reference count number, m underscore or whatever it is. This is actually one way that you could do it safely. That is, the object has been constructed and nude and everything, but it hasn't been released to the outside world yet. The outside world has been passed, has passed in a buffer, right? That buffer might be a pointer to a global variable, right? So here that variable passed in is being assigned this pointer, and then a reference is being added, right? So close to getting it right. if only this line came first, then it would be safe, right? Because once this line occurs, it doesn't matter if the function even returns. Try to imagine there's a global object, GP client of something, right? My interface, right? And then in some function, it's supposed to build a GP client, right? So the function calls, maybe you have another interface or something. In fact, I think the call is co-create instance. Blah, 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 and then at the end, address GP client, right? Thread 1. No, it's in thread 2 somewhere in the universe. Oh, I don't know, something like assuming that, let's suppose there might be a critical section associated with this thing, right? But if there isn't, or maybe they don't even care, because they might consider this, and it is in fact, I think, safe. Is it safe? No, it's not safe, but they might do something like this. Start working with it, one thing that they could do is add a reference count to it, right? And then safely work with the object, knowing that it's not going to get deleted. This is like a malloc almost. This is malloc, and release is delete. Okay. Now you have to just imagine wherever that line went. Here, right? This assignment occurs, and here at this point, task switch, so we don't get in here yet. So the PPV GP client is not null. We've assigned a value to it, but it has no reference count. Task switch to thread 2, which adds a reference to the client, does some work, and then releases it. Whereupon release gets called. Release is in here, I think. No, in here. Release. Managed to get through all the bugs. Count goes down to 0, and the object is deleted. Then we switch back to thread 1, right? And we go back here, we're back into co-create instance, where we go to increment our reference count, wherever it is, and we get a crash. Right? We haven't even left the function. The function that assigns this thing and we've got a crash. Something got in, bumped the count up, bumped it down, and deleted the object before we had a chance to add a reference count to it. Because this is the line that gives it to the outside world. It doesn't matter if the function has ran a return instruction. The assignment is happening here. It's not happening on the stack as one would usually like it to happen, but you can do that safely by adding the ref first, right? Now, if this assignment takes place and somebody happens to jump in and start using the thing, they could do that and they can release it, but it won't get deleted, right? It's bad enough that they could get in, but that sort of thing does happen. But there's no chance of any of this happening if the reference count started out at 1, right? And that was one of the things I realized recently, because I was looking at add ref in general in well, maybe it wasn't this project, something else, and I was thinking, well, geez, add ref is dangerous, right? I mean, you can't count on the object surviving long enough for you to add that reference, but you can, though, if it starts out at 1, right? When an object is constructed or new, you say object equals new my class, right? The assignment of the pointer value created by this new operator occurs after the object is constructed. So if during the course of its construction its reference count is 1, then by the time the assignment completes, by the time there's any data here available to the outside world, then the reference count has a value of 1, and it's impossible for it not to have a value of 1, and so therefore the reference count must start at 1, and there's no need for this add ref line at all. You don't need it. It goes away, and you can do this safely. Now it could be something that occurs. Well, this thing happens to be on the stack, right? But it's a pointer to something else, and that thing that it's pointing to, it's not usually a stack variable. It can be, but it could be global as well. But I undid all those changes because this is such a prime example of all of the standard wrong things people do in a multi-threading context, because they haven't acquired painfully the years and years of experience that really put the fear in you when it comes to multiple threads. And tracking down a bug that has to do with something like a race condition, or the interchanging of those 2 lines, for instance, is next to impossible. And if it's something that's causing a crash all the time, and it's subtle enough that you can't find it. Sometimes the only solution is to just scrap everything you've done, for the past 6 months or something, and go back to a point where you know things were working. You see this program here? If I want to crash this program, all I gotta do is press this button. About 70% of the time it crashes because it's got 2 threads running, right? And the programmers obviously don't have a feel for synchronization and the things that can happen. They're thinking linearly, like the person who wrote this is thinking in a linear way. That's human nature. We all it's natural for us to think that this line happens, this will happen before this, and then this will happen before this. It's going in a linear way. But in a multi-threading environment, it doesn't work that way. All of these lines are being executed all the time, right? In every possible order. That's the way you should think about it. Think that every single line is currently executing. And then you'll maybe build some appreciation for the danger. I'm sure I could find more, but I went back and looked at my own code and I saw that I'm doing that, and I tried changing it, but I'm too afraid of breaking something else. My smart pointer class has, oh no, I did change it. And what did I do? How did I fix it? Because it can't start as 1 in my case, because of the way that this object is always used. You knew something and pass it in, and you don't have to decrement any counters. So how come this would work? Oh, I see. Now is that going to happen? That's going to cause this one. Now I don't see how this line could ever get executed. T can be anything, unfortunately. Could be a rest star. This turns it into one of these, which increments a count. But that would be, in the case of an assignment, that would be a temporary, so that would go back to, it would go up to 2 and then down to 1. I don't think it's possible. There's nobody has access to this line. I could get rid of it. I thought I undid it. The idea of that was, if it's one of these objects already, then you do have to increment it. If it's one of these objects, then you don't. But it's never going to be that. Let's see now. Copy construct. There is no copy construct. Okay, actually I think it's fine. I'm going to try it. For one of those smart pointer things, I need a class that derives from ref, usually private, it has to be private, really. Maybe it holds I don't know, a buffer. This is the reason why you would use a smart pointer. Maybe it's a number and a second argument to int size and a value to fill it with. Value. I don't think I need to cast it. Right? And I'll delete. That's this is like the kind of class that is vulnerable to being wiped out by copy. The default copy constructor will kill it. So these objects are no good on their own. It's better to make a smart pointer H1 instead of P. Now this is one way to do it. 30 days. Right? Now I can copy that around all I like, and I won't lose the data. Well, how about this? Terminal terminated. What's the guy who's Calic? Okay. Who takes smart pointer to an L? SPANP. That should work. I'll put this in scope. It should all happen correctly, and the object should be dead by the time I get here. Looks like I made a mistake somewhere. Looks okay for a quickie. No default constructor, that's fine. not using it. What have I done wrong? Private, oh, struct. Oh, I have to make a friend of someone. I think that should do it. Because refs needs to be accessible to this thing. Cannot convert from. Oh God. That's a little bit too strict. So now this is a ref star, and this will use no, it's going to have to use the copy constructor, so it's going to have to convert this into a ref ptr, right? Which will give it a reference count of 1, but by this line it should lose that count. So for a little while it'll be 3. First let's go for the new. Nothing's assigned yet. While I'm doing this part. That's the H owl. What about, oh, it's temporary, it's on the stack. Now this will convert that to a ref ptr using this constructor. Ooh, maybe I learned something. It's 1, that doesn't seem right. Count is 1. Well, that's correct. I mean, it should be 1, right? So I found an answer. Okay, well that's one way to do it. But let's see now. We step into the function. We should have a 2, which it does. We step out. Should 1, and this should delete. No, see. Well, that might not. That might just be a bug here. It is a bug. Okay, so suppose I just declare this and set it here. It's a different scenario because it's not it's going to use an operator equals instead of an assignment copy constructor thing. But that should be okay because in this case I don't think it's going to go to the other constructor for ref ptr. Alright, so H Allen is just nothing. A new. Okay, building an Allen. Oh, it's not assigned yet. Okay, now this is building a Allen on the right hand side. I mean a ref PTR on the right hand side, and its count is when is 1. This has a count of 1. And now an assignment is going to occur. And we didn't see it happen, but temporarily, if I go into the disassembly, this assignment increased the reference count on this to 2, right? And then this thing went out of scope, and that decreased it. I have to do it slowly to show you it happening. Well, not slowly. I'll put a breakpoint on the copy line. See, here is our Allen coming in, who has a count of 1. This object has nothing. Acquire the object and then increment. So now the count is 2. So, oops. So after the assignment, the count is 2. But then when we get before getting to this line, there's a destruct, right? That temporary, which was assigned, is now being destroyed. Count 2. And so it worked. So I solved it. I'd forgotten. I found a way. But I didn't go through this test. This particular test, it's good that I have. So in both cases, copy constructor or assignment, the number of references is 1. At no time is it 0, and that's the important thing. If it's 0, at any time when it's in a variable that some other thread can access, then that thread can bump it, do what I said before. It can bump it up and drop it down, and then the object gets deleted before the before the next line. That would happen, let's say, if it started out at 0, right? An assignment occurs. I meant to increase it, right? That's what the code that was there before would have increased it after assignment, and then, but that's too late. The object would have been destroyed. Now another delete. It shouldn't crash this time, as I fixed my bus. Great. Well, I hope you learned something about multithreading. It's very important to be very careful with threads. Just think, like I said, all lines are being executed at all times, and the amount of time between one line, from one line to the next, is always 1,000 years. And if you follow those principles and just accept that as being the truth, then you'll find your bugs, I think. See ya. I forgot to add one thing to this. You might, looking at what I was showing you there, you might be thinking that, if it's multi-threading, then you can't touch or look at anything, any variables that, and so essentially you need a critical section around every function. That is one way of doing it, but the more common method to bring things back to a situation where things are linear and you can think in the normal way is to use marshalling. Is to marshal the calls to any struct or class that is used in multiple threads, so that the calls occur in a separate thread all of its own and happen in a linear way. And it's exactly the same mechanism as was used with that pick view. And that's the one step. One thing that's missing from my little device class is a marshalling option to allow for all the calls to occur in one thread. It might not be one thread. It could be something like that server thing where each client has one thread associated with it, and each client is associated with only one object, if you know what I mean. In that case, the client is another process, right, and has a dedicated object all for themselves, and a dedicated thread, and all of those calls would happen in their thread synchronously or in a marshaled form, and similarly for any other clients. And that's the real answer, because having to just wing it with critical sections and signals and stuff is far too complicated, and that's the way it's normally done. That's what Windows WindProc is an example of a marshaled function. You never have to take any special action to guard against multiple threads in a WindProc. You'll never see in a WindProc something like, enter critical section. Well, you might, but it would be highly unusual, and it would be something happening outside of the operating system's callbacks. Okay, just wanted to add that. See you.